Alright, so in a second I'm going to lecture on section 4.8. Before I jump into 4.8, I wanted to do just a couple of review problems just to make sure you haven't forgot some of the skills in 4.6 and 4.7. And I'll pick the things that your calculator can't do, and that would almost certainly be on any test I'd give over chapter 4. So this is the first one's kind of from, this is more of a section 4.6 kind of problem. Definitely this is a flavor of something you might see on a test. The numbers in this problem might be a little bit larger than I'd put on a test, but the style of problem is definitely test-worthy. So this is an adding problem with cube roots. And in order to add cube roots, you have to have the same numbers under the cube root. And that's not the way this problem is presented to me. This probably means that both the cube roots are reducible. So I'm going to try to reduce the cube root of 54. First I'm going to do a prime factor tree for 54. And this tells me, my calculator tells me, that 54 equals 2 times 3 times 3 times 3. So that tells me the cube root of 54 is reducible, and that I'll get a 3 outside the radical and a 2 under the radical. So for the first 54 piece, I'm going to write a 4, and then a times 3 for the 3 3's in the prime factoring of 54, and leave a 2 under the radical. I could simplify that more, and I will in a second, but I'm going to do the same thing for the 686. 686, its prime factoring is 2 times 7 times 7 times 7. So for the 686 factor, I get a 7 outside the radical and a 2 under the radical. So I'm going to bring down my plus sign. The 6 that's in front of that radical is going to stay there. I'm going to get a 7 in front of the radical and a 2 under the radical, because anytime I get 3 of a kind, I get 1 out front. Anything less than 3 of a kind goes under. And now I'm almost done. Now I'm going to multiply this 4 and that 3 and get a 12 cube root of 2. I'll multiply this 6 and that 7 and get a 42 cube root of 2. Now, because they're both cube roots with a 2 under the cube root, I can add these together. And I add these by just adding the numbers to the left of the cube roots. 12 and 42 add up to be 54. So an answer to this problem would be 54 cube root of 2. My calculator can't do that. But what my calculator can do is it can do decimal versions of the original problem and decimal versions of the answer. So if I wanted to check, best thing to do for this would find a decimal version of the original problem. So 4 cube root of 54 plus 6 cube root of 686. The decimal version of the original problem is 68.0357. If the decimal version of my answer is also 68.0357, I know I'm correct. And if it isn't, I've messed up. So let me try my answer now. So my answer is 54 times the cube root of 2. And 54 times the cube root of 2 is the same 68.0357. So as long as the problem doesn't have a letter, even though I might not be able to solve the problem on my calculator, because doing this on my calculator gives me that, I can still check using my calculator. So that's kind of the flavor of the section 4.6 problems that will make their way onto the chapter 4 test that you have coming up. And then in section 4.7, which is the multiplying section, the big trick kind of problem, and I'll make it have an X because I don't want my calculator to be able to do this, would be something like this: 3x plus, it's too complicated. Let's make it less complicated. How about this? X plus the square root of 2 quantity squared. So this is a review from section 4.7. I mean, it's only one problem, but this is the one style of problem that comes from that section that students tend to mess up on the test. So this problem, although it doesn't look like a foiling problem, when I write it without the square, you can see more clearly that it's a foiling problem. And this is going to be a horrible, messy foiling problem. So I'm going to do firsts, which are x times x. Outers are x times square root of 2. Inners are square root of 2 times x. Lasts are square root of 2 times square root of 2. This is probably a notch more difficult than I would give on a test, but it's good for you to see the difficulty here, because if you're going on to 151 or 212 or 220, calculus or college algebra, math just gets harder. So just to be exposed to some things that are a little bit harder is not so bad. So firsts are easy. That's x times x. It gives me x squared. Outers and inners, I'm going to get positives, and unfortunately, I can't multiply a letter or something outside a square root with something under a square root. So both of those I'm just going to write as x times the square root of 2. This is going to be the tricky part, knowing what to do in terms of simplifying the x square root of 2 pieces. The lasts are easy for me. The last square root of 2 times the square root of 2 would be plus square root of 4, and that would just simplify to plus 2. I'm almost done. The tricky part is knowing how to combine these, because these both have the square root of 2, so they can be added, and you add these together by adding the stuff outside the radicals. And if you're clever, you can add these without me pushing you in the right direction. But if you've never seen this before, that would be being really clever. So I'm going to emphasize that each of these x square root of 2's has an imaginary 1 in front of them, and what I'm going to add is a 1x and 1x. I'm going to get a 2x. So for my answer to this problem, to multiply this out or to FOIL that out, the 3 pieces I'm going to have is an x squared, and then I'm going to get a 1x plus 1x is 2x, and when you're adding, the square root part doesn't change, it just kind of hangs out, and then the lasts are going to stay that too. So both of these are, test worthy. The first one, the numbers are probably a little bit bigger than I would give on an in-class test, but still the style is okay. And in this problem, I probably wouldn't put the x in. I'd probably give you something that's more calculator friendly. But you should definitely be able to do both of these problems by the time we get to the test. So the nice thing about section 4.8 is that on a lot of the problems I can do on my calculator, and they're not that hard even if you don't have a calculator handy. So the first 22 problems, the instructions say rationalize the denominator. Rationalize means to write an equivalent fraction, or an equal fraction. I guess equivalent's probably a better word. That doesn't have a radical in the denominator. For our purposes, there's kind of 3 styles of problems that we're going to do. In the first 1 through 22, 2 of the styles appear, and then in the last 23 on, the last style appears. So the first style of problem they have monomials in the denominator and square roots. And that's kind of up through 14. All the problems up through 14, if you look at the denominators, there's a square root, and there isn't any pluses or minuses, or there's a monomial as opposed to a binomial. So if I broke the categories down, 1 through 16, the denominators, they have what they have in common is they have square roots and monomials. The next group of problems, so it probably means 1 through 15, because 16 it changes. At 16, 18, 20, 22, there's only a single term in the denominator, but it's a non-square root. So kind of 16 to 22, the denominators still have a monomial, but they have, a non-square root. They might have a cubed root or a fourth root. For what it's worth, I've never put one of these on the test, so I doubt that I would start anytime soon. The third category of problems in this section have binomials in the denominator and they're only square roots. So 23 through 34, if you look at the denominator, it has two terms separated by either a plus sign or a minus sign. And most of the ones between 23 and 34 only have square roots. They don't have letters. It means my calculator can do those. So the last style of problems, 23 through 34, they have binomials in the denominator. And so each one of the categories I solve by hand differently. If I could enter it on my calculator, then they're not different at all. For instance, my calculator, if I entered the fraction 2 over the square root of 7, it is programmed to write an equivalent fraction that doesn't have a radical in the denominator. It's programmed to rationalize denominators because it's a common thing that mathematicians want. So I'll be able to, without even understanding how to get to the answer, I'll be able to tell you the appropriate equivalent fraction by just creating a fraction and going 2 over square root of 7. And my calculator tells me 2 over square root of 7 reduces to 2 square root of 7 over 7. When I say this is an answer, this means this fraction and the original fraction are equal to each other, but the rewrite has the square root in the numerator as opposed to the denominator. To get there, for each of the problems between 1 and 15, possibly, I don't know what 15 is because I don't have it written in front of me. For each of the problems between 1 and probably 15, they have monomials with square roots in the denominator. To get by hand from the problem to the answer, you're going to multiply by the denominator over itself. Because multiplying a fraction by something over itself, it's multiplying a fraction by 1, which changes the way the fraction looks, but doesn't change what it reduces to. So for problem 2, to get to what my calculator says the answer is, I multiply the numerator and the denominator by the denominator. The multiplication in the numerator, there's nothing I can do. I just leave the 2 and the 7 next to each other because I can't multiply a number outside a square root with a number under a square root. In the denominator, if I want it to be inefficient, I'd multiply the 7s, leave them under the square root, and then I know the square root of 49 is 7. But if I didn't know the square root of 49 was 7, I could use my calculator. Because it's a perfect square root, it would do it nicely for me. So that matches up perfectly to what my calculator gave me. And it basically took one step to get there. As a matter of fact, I could have skipped this intermediate step, because anytime I'm multiplying two identical square roots, what's ultimately going to happen is the square root, when you get it completely reduced, it's going to reduce to what's under one of the square roots without the square root symbol. So for each of the problems between 1 and at least 14 that I'm going to do by hand exactly the same thing. I'm just going to multiply by an exact copy of the denominator over itself. I'm going to get an intermediate step that I'm going to reduce to the final answer. If the problem doesn't have letters, then it'll take me straight to my answer if I just bust out my calculator. If it does have letters, then I'm bound to do it by hand. But structurally, there's no adding or subtracting in the denominator, and there's a square root as opposed to a cubed or a fourth root. And for each of those problems, you do exactly that. Just multiply by a copy of the denominator over itself, and then reduce. So 4 is similar. I'm going to do it by hand first, and then I'll use my calculator. So to get a rationalized equivalent fraction, I multiply by a copy of the denominator over itself. The numerator, I'm not allowed to multiply a number outside a radical with a number under a radical, so I leave them written next to each other. The denominator, I should be efficient. If I want it to be inefficient, I'd multiply the 10s because they're both under the radical. I'm allowed to multiply them. 10 times 10 is 100. And then if I did reducing the denominator, the square root of 100 turns into a 10. So ultimately, we usually get a little bit efficient. And we use the trick that if you're multiplying two identical square roots, rather than showing the intermediate step of multiplying the numbers under the radical and then reducing, if you're multiplying two identical square roots, what's going to happen is it ultimately will reduce to what's under one of the radicals without a square root. This fraction, although it's equal to the original fraction, it's not reduced because the 5 outside the radical will reduce with a 10 outside the radical. The 5 turns into a 1 when you reduce it with a 10. The 10 turns into a 2. And my calculator wouldn't show that 1 in the numerator, so I won't show it either. I'm going to say the answer, the reduction of this that's equal to the original problem, is the square root of 10 over 2. I'm going to try to do this on my calculator to make sure I'm okay. So I'm going to go fraction 5 over square root of 10. Hopefully when I hit enter, I get the square root of 10 over 2. And I perfectly did that, so I know my work is perfect and I checked it all I need to check it. 6 is where it gets worse because of the letter. I can't do this on my calculator. But it's in this first 14 or so problems that have no adding or subtracting in the denominator, and the denominator has a square root. And for each one of these problems, I'm just going to multiply by an exact copy of the denominator over itself. The numerator, I can't multiply something outside a radical with something under a radical. It means I'm not going to get a 50 there. I'm just going to leave the 5 outside the square root and the 10x under the square root. If I wanted to in the denominator, what I should do is just write that. Because I'm multiplying two identical square roots, it's more efficient to not show actually multiplying what's under the square roots. But if I multiplied the 10x times 10x, I'd multiply the 10 times 10 and get 100. I'd multiply the x times x and get x squared. And then I would do the square root of 100, which is 10, and the square root of x squared, which, because it has a pair of x's, it's just x, and it would reduce to 10x. But this intermediate step, we just shouldn't show. And we'll skip it every time in the first grouping of problems. Anytime you're multiplying two identical square roots by themselves, you can skip the multiplying part, write what's under one of the square roots without the square root. The 5 and the 10 here are reducible again because they're both outside a radical. There's no adding or subtracting in the denominator, so it's legal to cancel. The 5 cancels to 1. The 10 cancels to 2. I can't cancel the something under a radical with something outside a radical, so I can't cancel the x's. So for an answer to this, I'm going to write the square root of 10x over 2x. And again, you can't cancel the 10 with the 2, nor the x with the x, because you can't cancel something outside a radical with something under a radical. 8 and 10 aren't my favorite because I can't do them on my calculator, but they're not terribly hard. So I'm going to do just like I've done for the first 3 problems. I'm going to multiply by an exact copy of the denominator over itself. And this only works when the denominator has a square root without any adding or subtracting. When I do the multiplication in the numerator, I just write the x to the left of the square root of 5x. I can't multiply things outside radicals with things under radicals. The denominator, I'm multiplying two identical square roots. So I'll speed through that multiplication and do the shortcut. Anytime you're multiplying two identical square roots, ultimately what it's going to reduce to is what's under one of the square roots without the square root symbol. And now I'm going to cancel again. The x in the numerator outside a radical could cancel with the x in the denominator because there isn't a plus or a minus. If it was like x plus 5 or x minus 5 in the denominator, I couldn't cancel the x's. But since there's only multiplication in the denominator, I can cancel the x's. So for an answer to this problem, it's going to be the square root of 5x over 5. And you can't cancel a 5 outside a radical with a 5 under a radical, so I'm done. 10 is the same structure, so I'm going to multiply just by the denominator over itself. So I'm going to multiply by the square root of 2b over the square root of 2b. In the numerator, just like every problem so far in this grouping, I can't multiply something outside a radical with something under a radical, so I leave them next to each other. In the denominator, anytime I'm multiplying two identical square roots, I can skip and go right to the result. I'd get what's under one of the square roots without a square root symbol. In this problem, both the 2 and the b are going to cancel. I'm canceling the entire denominator, so my answer doesn't need to be a fraction. And you get the square root of 2b. It seems to me if you have to take trig, Math 182, rationalizing denominators comes up a ton in that course. So definitely you see a bunch of it if you go to 182. You'll see a little bit in 151 if you go to that for your next math class. You won't ever see it in 142 if that's your next class. 12 is tricky. 12 has a radical that's reducible. I'm going to, at some point I need to reduce the radical. I'm going to hold off on reducing. I'm going to treat 12 just like any problem that I've done so far. Any problem that just has a single square root in the denominator without any adding or subtracting. You can get the fraction rationalized by multiplying by an exact copy of the denominator over itself. In the numerator, I just leave the pieces next to each other because I can't multiply something outside a radical by something under a radical. And in the denominator, you get that 6x cubed. When I look at that 6x cubed, the 6 doesn't reduce because it doesn't have any pairs. But the x cubed does reduce because if I write x cubed out, I get a pair of x's and an x left over. So in the numerator, that 6x cubed is going to reduce to have an x outside of the radical and an x under the radical. I set my denominator up to cancel to make the canceling clear. So in terms of reducing now, this 8 and that 6 reduce by 2. 8 goes to 4, 6 goes to 3. I could cancel an x, and what I have left is going to be my answer. In the numerator, I have a 4 to the left of the radical, a 6x under the radical. In the denominator, I have a 3, and then the 2 x's that are left, I'm going to write as x squared. So none of these problems are calculator friendly because they all have that x that's messing me up. 14, I'm going to do the same thing that I've done for every problem so far. I'm going to multiply by an exact copy of the denominator over itself. So I'm going to multiply by b to the 5th under a square root times b to the 5th under a square root. In the numerator, I'll get a 2 times the square root of b to the 5th. In the denominator, I get a b to the 5th without a square root symbol. And that b to the 5th in the numerator, since it's under a radical, I need to attempt to reduce it. And to reduce that, I'm going to get 2 b's outside the radical and 1 b under the radical. So in the numerator, because the square root was reducible, I should reduce it. And the b's that I brought outside the radical will reduce with a couple of b's in the denominator. And my final answer in the numerator is just going to have a 2 to the left of the radical, a b under the radical, and after I cancel, I have 3 b's left, so I'm going to have a b cubed in the denominator. And you can't cancel the b's because you can't cancel something outside a radical with something under a radical. So if you hit the fast forward button and fast forwarded to where I did 23 through 34, it's not going to impact you on the test. If you're going on to Math 151 or 182 for your next class, it couldn't hurt to watch these, but it's not going to be horrible if you skip them either. They're not really prevalent in higher classes. The big difference between what I've done so far and problem 16 is this is a cube root as opposed to a square root. And again, I'm not going to ask you to rationalize a cube root or a fourth root on the test. The difference algebraically is it's not enough to multiply by one of the denominators. When you have a cube root, you have to multiply by two of the denominators because you need three of a kind for a cube root to reduce. So what I'm going to do in this problem is I'm going to multiply by two copies of the denominator. I don't know why I did that like that time sign there. So I'm multiplying by two copies of the denominator. In the numerator, the 3 that's outside a radical can't be multiplied by the radicals. The 2's under the radicals could be multiplied together. So I get 3 cube root of 4. In my denominator, I multiply this 2, and that 2, and I get a cube root of 8. And the cube root of 8 in the denominator, the cube root of 8 in the denominator is just 2. Anytime you multiply 3 identical cube roots, ultimately what it's going to reduce to, it's what's under one of the cube roots without the radical symbol. So I claim this is my answer. This is a fraction that's equal to the original fraction that doesn't have a radical in the denominator. Easy enough to check. Although my calculator can't do this problem, it can give me a decimal equivalence for the original problem and a decimal equivalence for the answer. Those decimal equivalents have to be the same for my answer to be right. So I'm going to take this original problem, 3 over the cube root of 2. Its decimal is 2.3811. And then I'll do the same for my answer, fraction 3 cube root of 4 over 2, and get a decimal equivalent for that. Since they have the same decimal equivalents, they're equal to each other or equivalent to each other, and I've rationalized. I've taken a problem that had a radical cube root in the denominator, wrote something that's equal to it that didn't have a cube root in the denominator, and winds up going to the numerator. So when you have a cube root, a way to reduce it is to multiply, instead of by one copy of the denominator, you have to multiply by two copies of the denominator. Because then you'll have a 3 of a kind, and when you have 3 of a kind, it makes a perfect cube. So if I was doing 18, and I'd multiply by 2 cube roots of 9 to get me something that's reducible. In the numerator, the multiplying that I can do is I can multiply the 9's together because they're both under a radical, and when I multiply those I get an 81. In the denominator, I go 9 times 9 times 9, and I get the cube root of 729. It's always going to be the case when I'm doing these that the radical in the denominator is going to go away. So if I do the cube root of 729 on my calculator, I can reduce the denominator just to a plain old 9. So the denominator, because I multiplied 3 identical cube roots, reduces to what's under one of the cube roots without the cube root symbol. The numerator, I have a cube root of 81. I think that's reducible cube root. So I'm going to do a prime factor tree for 81 to try to reduce the cube root of 81. So the 81 is equal to 3 times 3 times 3 times 3. So in the numerator, that 81 that's under a radical reduces, and it reduces to get a 3 in front of the radical and a 3 under the radical, because there's 4 3's. 3 of them come out as 1 3, and the other one stays in. And now I'm going to multiply that 6 and 3 that are outside the radical, and I get 18 cube root of 3 over 9. The 18 and the 9 are reducible because they're both outside a radical. The 18 turns into a 2, the 9 turns into a 1, so my answer doesn't have to be a fraction. So my answer for problem 18 is going to be 2 times the cube root of 3, because 18 reduces to a 2 when you do cancel with a 9. I'm going to do a decimal equivalent for the original problem. So the original problem is 6 over cube root of 9. The original problem is 2.884499. And I'm going to do a decimal equivalent for my answer. So I'll go 2 times the cube root of 3. And I get 2.884499. Because my original problem and my answer have the same decimal equivalents, I know they're equal to each other, and I know my answer is correct because it doesn't have a radical in the denominator. For each problem in this section, my goal is to write a fraction that's equal to the original fraction that doesn't have a radical, square root, cube root, fourth root in the denominator. So 20, if I want to reduce it, because it's a cube root, it's not enough just to multiply by one copy of the denominator. I need to multiply by 2 copies of the denominator. In the numerator, because both the 2x's are under the radical, I'm allowed to multiply them and leave them under the radical. So I'm going to get 3 times the cube root of 4x squared. And in the denominator, anytime you multiply 3 identical cube roots, ultimately what it's going to reduce to is what's under one of the cube roots without the cube root symbol. So I sped up a little bit, especially because this is not going to be on the test. I think I'm done. The 3 and the 2 can't cancel. I can't cancel a 2 outside a radical with a 4 under a radical, nor can I cancel an x outside a radical with an x squared under a radical. You can't cancel outside a radical with under a radical. And under the square root, the cubed root, the prime factoring for the 4, only has a pair of 2's. The prime factoring for the x only has a pair of 2's. I don't have any 3's of a kind, so this is going to be the answer. And again, I'm not going to have you write a problem that has a cube root in the denominator without a cube root in the denominator. It's just not something that's that important to me. It just doesn't come up that much in higher math. 22 is the next level of difficulty. I have a fourth root, and in order to get a fourth root out of a denominator, I need 4 of a kind, which means I have to give it 3 more fourth roots, because if you have 4 fourth roots of the same, they're going to wind up canceling. So in square roots, I just needed one copy of the denominator to bring me up to the 2 copies that will reduce the square root. In a cube root, I needed to add another 2, and in a fourth root, I need to add 3 copies of the denominator. If I wanted to do this in the numerator, these 3's I multiply. 3 times 3 times 3 is 27. They're going to stay under the radical. In the denominator, all the 3's are under the radical. So I'm going to multiply 3 times 3 times 3 times 3 and get an 81 under my fourth root. Fourth root of 81 is going to be perfect. I'm going to do that on my calculator. I'm going to give my calculator the chance to do the fourth root of 81 for me. The fourth root of 81 is 3. And anytime I multiply 4 identical fourth roots, I could actually speed through it, skip this middle step, because it's always going to reduce to what's under one of the symbols, fourth roots, without the radical sign. I'm almost done. The radical in the numerator doesn't reduce because the prime factoring for 27 only has 3 3's. It doesn't have 4 3's. And in a fourth root, you need a 4 of a kind for it to reduce. The 3's will cancel, and for an answer that I believe is correct, I'm going to say it's the fourth root of 27. So now I'm going to do a decimal equivalent for the original problem, decimal equivalent of my answer to make sure they're the same. So original problem is 3 over the fourth root of 3. Decimal equivalent for the original problem is 2.2795. and I'll do decimal equivalent of what I say my answer is. So 4th root of 27, 2.2795. Because my answer and the original problem have decimal equivalents, they're equal to each other, and because my answer doesn't have a radical in the denominator, my answer is good. So far, what I've done, every problem I've done has only had a monomial in the denominator. If you look at problem 2, there wasn't a plus or minus sign, there was a square root, so I multiplied by a copy of the denominator over itself. 10, at 4, there wasn't a plus or minus sign, it was a square root, I just multiplied by one copy of the denominator. Same thing with 6. Only a square root in the denominator, I multiplied by one copy of the denominator. 8, just like so up through 12, actually up through 14, I did them exactly the same way. I just multiplied by the denominator over itself. The next few problems, 16, 18, 20, the denominators had not square roots, so I needed more than one copy of the denominator. I needed to get a total of 3 copies of the denominator to simplify a cube root, so I added 2 cube roots to give me the 3. Similarly, in 18, I needed 3 copies of the denominator for it to reduce. I had 1, so I gave 2 more. Same thing in 20. I had 1 copy of the denominator. It was a cube root. I needed 3 copies of the denominator. I gave it 2 more. 22 is a 4th root. For the denominator to reduce, I need 4 copies of the denominator. I start out with 1. I needed to give it 3 more. All the problems up through 22, although they got progressively more complex, they didn't have any adding or subtracting in the denominator, so all I was doing was multiplying either by the denominator or copies of the denominator. Once we get higher, it's not going to be proper to just multiply by the denominator over itself. I'll have to multiply by the conjugate, which is the denominator with the sign changed. So the big step up in difficulty is when the denominator has a plus or a minus sign. In every problem between 23 and 34, the denominator is a binomial, and it has either a plus or minus sign in it, and it's absolutely going to be wrong just to multiply by an exact copy of the denominator over itself. So you do not, on this problem, multiply by 6 plus square root of 3 over 6 plus square root of 3. That's not the conjugate, and that will not give something that's equal to the original problem that doesn't have a square root in the denominator. If I did this, if I multiplied by 6 plus square root of 3 over 6 plus, so I'll show you that this is what happens if you do that. If I do 4 over 6 plus square root of 3, if you did this, multiplied by 6 plus square root of 3 over 6 plus square root of 3, the numerator, I'd go 4 times 6 is 24. 4 times square root of 3 is 4 square root of 3. The denominator I FOIL. Firsts in the denominator are going to be 6 times 6, which are 36. Outers are going to be 6 times square root of 3, which is 6 square root of 3. Inners are going to be square root of 3 times 6, which is another plus 6 square root of 3. Lasts are square root of 3 times the square root of 3, which is the square root of 9, which is 3. If I did what I'm not supposed to do and reduce, I get 24 plus 4 square root of 3. This 36 and that 3 add up to 39. And this 6 square root of 3 plus that 6 square root of 3 give me 12 square root of 3. Multiplying by a copy of the denominator over itself, it gives you a fraction that's equal to the original fraction, but it still has a square root in the denominator, and that's not my goal. My goal is definitely to write something equal to the original fraction, but not equal with still a radical in the denominator. Let me show you what the answer is going to be, and then show you how to get there. So my calculator, because this only has fractions, it only has square roots and it doesn't have letters, it doesn't care that the problem's a step a little more complicated. It knows how to reduce this properly, and my calculator tells me that this reduces to 24 minus 4 square root of 3 over 33. Sometimes when I do these by hands, I get the answer, the numerator, backwards. So that's the answer I'm striving for. That's definitely not what I got when I multiplied by 6 plus square root of 3 over 6 plus square root of 3. It's the wrong thing to do. The right thing to do is to multiply by the conjugate of the denominator, and the conjugate of the denominator is the denominator with the signs flipped. Because the denominator started off with a plus sign, what I'm going to multiply is by the denominator over itself with the sign flipped. So there's just that subtle difference. Multiplying by the denominator over itself reduces to something that's not the correct answer. Let me show you that multiplying by the denominator with the sign change does. So I'm going to do the numerator. There's two multiplications I need to do in the numerator. First multiplication is 4 times 6. The 4 times 6 gives me the 24. Second multiplication is 4 times minus square root of 3. For that, a positive times a negative is a negative. I leave the 4 and the 3 next to each other. And magically, you look at that and that, they look the same. Now I'm going to work on the denominator, which is a foiling problem. So for the denominator, I'm going to FOIL. I'm going to go 6 times 6, which is 36 for the first. The outers are going to be 6 times minus square root of 3. Positive times a negative, so I get a negative. I can't multiply something outside a square root with something under a square root, so I just leave them written next to each other. Inners are going to be square root of 3 times 6. They're both positive, so I get a plus sign. And I'm going to write plus 6 square root of 3. And then the lasts are a positive square root of 3 times a negative square root of 3. Positive times a negative is a negative. Technically, it comes out to negative square root of 9. But I'm just going to write minus 3 because that's what square root of 9 is. In the denominator, these cancel because they're opposites. To reduce the denominator, I just take the 36 and the minus 3, and they reduce to the 33. So you can see how I have the correct numerator, and simplifying that gives me the correct denominator. So my answer is going to be exactly what my calculator said it's going to be. 24 minus 4 square root of 3 over 33. I'm going to do 26 by hand and then on my calculator. 26 by hand is a little bit harder than the last problem, but not ridiculously hard. Because I have a denominator that has a plus sign in it, and it has square roots, to rationalize the denominator, to write something that's equal to the original fraction, I'm going to multiply by the conjugate of the denominator. Generally, I usually completely reduce the denominator first and then worry about the numerator. So I'm going to do my denominator on the side, and then I'll worry about the numerator. The denominator is harder. It's foiling. Because sometimes the denominator cancels with the numerator, and if I multiply out on my first step, I might miss that canceling. So I'm going to hold off on my multiplying out my numerator just in case the simplified denominator reduces with the unsimplified numerator, because that happens sometimes. So in the denominator, I have to FOIL. So first are square root of 7 times the square root of 7. I know that anytime I multiply two identical square roots, I just get what's under one of the square roots without the square root symbol, because the square root of 7 times the square root of 7 is the square root of 49. The square root of 49 is 7. That's the first. Now I'm going to do the outers, which is square root of 7 times minus square root of 5. Positive times negative is a negative. And I'm allowed to multiply that 5 and that 7 because they're both under the radicals. Now I'm going to go to inners. The inners are a square root of 5 times the square root of 7. They're both positive, so I get a plus sign. The 5 and the 7 are under the radicals, so it's legal to multiply them. And then the lasts, a positive square root of 5 times a negative square root of 5. Positive times a negative is a negative. If I want to be inefficient, I multiply the 5s, get the square root of 25, and the square root of 25 becomes 5. I'm almost done with the denominator. My outers and inners are opposites, so they cancel. So what I'm left with when I simplify the denominator, when I FOIL it, is 7 minus 5, which is the first and the lasts. and that reduces to be 2. So what I've done now is not multiplied out the numerator, simplify the denominator. The single 2 that's left in the denominator will cancel with the single 6. The 6 will become a 3. And I'm not sure what answer my calculator is going to give me. It may give me this, or it may push the 3 through the parentheses. And multiplying the 3 through the parentheses, you just leave the 3 next to the 5 and the square root of 7. So my calculator is going to give me one of these, and I'm not sure which of these it's going to give me. So let me do this on my calculator now. So fraction 6 over square root of 7 plus square root of 5. It better give me one of these, otherwise I've messed up. Oh, and it gave me the bottom one. I thought it might not have that. It might actually do the multiplication and clear that parentheses. And they're both right. I'd live with either one of those. So the big deal in all the problems from 23 on is you have to multiply by the conjugate, or the denominator with its sign flipped. 28 I can also do on my calculator because it has square roots and no letters, but I'm going to do it by hand first, and then I'm going to check. I'm going to multiply by 8 minus square root of 5 over 8 minus square root of 5. I'm going to hold off on the numerator. I really don't think I need to do that holding off, but I'm going to hold off anyways. In the denominator, I usually do off to the side, because the denominator is foiling. It takes up a lot of room. So I'm going to FOIL the denominator. I'm going to go firsts are 8 times 8, which is 64. Outers are 8 times minus square root of 5, which is minus 8 square root of 5. Inners are the square root of 5 times 8, which is plus 8 square root of 5. The lasts are positive square root of 5 times negative square root of 5, which is technically negative square root of 25, which is minus 5. So firsts are 64, lasts are minus 5, the outers and the inners cancel. The 64 minus 5 is going to give me a 59. That 59 can't cancel with the square root of 5, so I'm going to multiply out the numerator. I'm going to go square root of 5 times 8. So for the numerator, I'm going to do square root of 5 times 8. And those you can't really multiply, but you can leave them written next to each other as 8 square root of 5. And then I'm going to do square root of 5 times minus square root of 5, which is going to be minus square root of 25, which is just minus 5. You can't subtract these and get a 3, because you can't subtract something outside a radical with something under a radical. This is what I get by hand. This should be a correct answer. I don't know if my calculator is going to flip the numerator on me. A lot of times the calculator flips the numerator. So when I do it on my calculator, if I get either of those answers, then I know I haven't made a math error. So let me attempt 28. So I want square root of 5 over 8 plus square root of 5. Hopefully I see one of these two answers. And I saw that, yeah, for some reason I just predicted that my calculator was going to do this, right, the square root piece second, but I'd live with either one of these. So again, every problem from 23 on, it has a plus or a minus sign in the denominator, and to get from the problem to the answer by hand, you have to multiply it by the denominator with its sign changed. If I'm kind and I don't throw a letter in the problem, then you can bust them out easy without your calculator. But sometimes I'm evil like I'm 30. So on 30, I can't check this on my calculator, so I just have to be ultra confident with my math skills here, because the letter makes it impossible to do on my calculator. So I'm multiplying by the denominator with the sign changed over itself. So I'm going to do again. I'm going to do the side work for the denominator. Get it simplified the best I can. And it's not going to simplify to just a single a letter or single number. It's going to be a binomial, unfortunately. So I'm going to do firsts in my denominator. First are square root of x times the square root of x. Anytime I multiply two identical square roots, I can skip a step, write what's under one of the square roots without the square root symbol. The outers are the square root of x times 5, which I'm going to write as plus 5 square root of x. The inners are minus 5 times the square root of x. I'm just going to write that as minus 5 square root of x. The lasts are minus 5 times 5, which is minus 25. The outers and inners cancel. In fact, when I'm foiling these problems that I've just done, I should really only do the firsts and lasts. But I'm being showing more detail than you have to show. The x minus 25 doesn't cancel with that 8, nor does an x minus 25 cancel with the x plus 5. So I'm going to multiply out the numerator. In the numerator, the multiplications I need to do are 8 times square root of x, which I'm just going to write as 8 square root of x, and 8 times 5, which I'm going to write as a plus 40. I can't cancel the 25 with the 40 because of the minus sign between the x and the 25 and the plus between the terms in the numerator. So that's going to be the answer to 30. It just can't be reduced. In order to reduce something that has an x minus 25 in the denominator, you'd have to have an x minus 25 in the numerator. When there's minuses or pluses between terms, the canceling becomes very restrictive. You only can cancel exact copies. 32 is a mess, as is 34 a mess, but I can certainly do them. The nice thing about 32 and 34, I can know what I'm shooting for. So I'm going to just cheat and do it on my calculator real quickly. I'm going to go 6 plus square root of 2 over 5 plus square root of 2. So my goal for an answer is going to be 28 minus square root of 2 over 23. If I get anything other than that, I'm going to be worried, unless I might get minus square root of 2 plus 28 over 23 for an answer. That I can live with. I'm not committed to having the 28 first and the 2 second. That would be the only variation of the answer that I'd be happy with. So to get from the problem to the answer, it's a mess. I have to multiply by the conjugate of the denominator, which is the denominator with its sign changed. And both the numerator and the denominator are going to be foiling. I like doing the denominator first, so I'm going to do that denominator. So for the bottom, I do firsts, which are 5 times 5, which is 25. Outers, 5 times minus square root of 2, which is minus 5 square root of 2. Inners, square root of 2 times 5, which is plus 5 square root of 2. Lasts, positive square root of 2 times minus square root of 2, which is minus square root of 4. So the 5 square root of 2's cancel. The first that's a 25, and the last that turns into a 2 reduces to my 23. So my denominator, I get the 23. Now I'm going to work on the numerator to get the 28 minus square root of 2. So I'm going to work on the numerator. Numerator is also a foiling problem because it's multiplying two binomials. So firsts, 6 times 5, which is 30. Outers, 6 times minus square root of 2 is minus 6 square root of 2. You can't get a 12 there. You can't multiply something outside a square root with something under a square root. Inners, square root of 2 times 5, both positive, so I get a plus sign, and I get a plus 5 square root of 2. Lasts, positive square root of 2 times a minus square root of 2 gives me a minus square root of 4. The outers and the inners combine. You just have to combine the minus 6 and the plus 5, and that gives me a minus 1 in front of the square root of 2. And then for the lasts are the numbers. I have a 30 and a minus 2 because the square root of 4 turns to 2, and 30 minus 2 is 28. So my numerator is going to be 28 minus 1 square root of 2, and you definitely don't need the 1, like my calculator didn't write the 1 there. So I actually have a variation of the answers that I said that were correct that I came up with by hand, because when I showed the 1 there, that's not necessary. So any one of these three would be acceptable for an answer. I can't remember putting a problem like 32 or 34 on a test in many, many, many years where you have to FOIL both the numerator and the denominator. So I would bank on, if I asked one of the bottom problems, probably something more like 26 or 24. Those are a little bit easier and probably more likely to pop up on a test. So last problem, 34. Since it has nothing but square roots, no letters, I can do it on my calculator. So I'm going to do 6 minus 2 square root of 3 over 6 plus 2 square root of 3. And apparently the answer wow, 2 minus square root of 3. It's not even a fraction. That surprises me and worries me, because when I get to the end of these lectures, no matter how long or short they are, my mind starts to just fade on me. And I almost did there. I have to multiply by the denominator with the sign change, so I need to multiply by 6 minus 2 square root of 3 over 6 minus 2 square root of 3. For whatever reason, I always do the denominators first. So for the denominator, the firsts are 6 times 6, which is 36. The outers are 6 times minus 2 square root of 3, which is minus 12 square root of 3. The inners are 2 square root of 3 times 6, which is plus 12 square root of 3. The lasts are positive 2 square root of 3 times negative 2 square root of 3, which is minus 4 square root of 9. So the outers and inners cancel. The lasts becomes minus 4 times 3. So I'm going to get 36 minus 12, which is 24 in the denominator. And that certainly doesn't look like I'm heading the right way, but I feel like I can get there. So now I'll work on the numerator. I'll try to squeeze it in to leave myself a little room. First in the numerator, so numerator. Firsts are 6 times 6, which is 36. Outers are 6 times minus 2 square root of 3, which is minus 12 square root of 3. Inners are minus 2 square root of 3 times 6, which is another minus 12 square root of 3. And lasts are minus 2 square root of 3 times minus 2 square root of 3, which is a positive. I multiply the 2's and the 3's and get a positive 4 square root of 9. So when I do this, I see 36 minus, these don't cancel. You add the 12's and keep them negative, so it's going to be minus 24 square root of 3. And my lasts are going to be plus 4 times 3, so it's going to be plus 12. So for my lasts, my 36 and my 12 are going to add up to be 48. So I get 48 minus 24 square root of 3 over 24. This would be nice if we'd done the quadratic formula, because in the quadratic formula, what we get in the next chapter, you learn how to reduce fractions like this. If the denominator goes into both sides of the numerator, it is legal and you should reduce like my calculator did. So the three things that I circled, I'm going to divide each by 24. I'm going to go 48 divided by 24 and get a 2. 24 divided by 24 and get a 1. 24 divided by 24 and get a 1 again. So the answer I came up with by hand reduces to 2 minus 1 square root of 3 over 1, and that's what my calculator gave me, except my calculator didn't write it as a fraction because the entire denominator canceled, and didn't write the 1 in front of the square root of 3. On the chapter 4 test, I would never put a problem that has this kind of reduction in it because we haven't really been exposed to it. But in chapter 5, we will do a bunch of reduction like this. I think it's section 5.3, it might be 5.2, that does the quadratic formula, the negative b plus or minus the square root of b squared minus 4ac all over 2a. And this kind of reducing a denominator with both pieces of the numerator comes up a lot in the quadratic formula. Again, the probability of seeing anything like 34 or 32 where you have to both FOIL the numerator and the denominator, I can't ever remember doing that. And even one of these problems with an x where you have to multiply by the conjugate, the chances of that coming up are pretty slim too. So in the bottom grouping, if you're just really good at the 24, 26, and 28 kind of problems, that's probably going to take you as far as you need to go. And then in the first kind of problems where we're just multiplying by a copy of the denominator or multiple copies of the denominator, you don't have to worry about the cubes in the 4 through problems. All right, so we're getting close to the end of this section. 4.9 is one of those monster long lectures that you're going to just have to deal with. It's in some sense a nice section because you can check all your answers real easily, but it's a long section and there's probably like 4 or 5 different styles of problems embedded in that section. So when you sit to watch that section, make sure you have plenty of caffeine and you're awake. All right.